Okay, so well, I guess on the title slide here you can see that there's a lot of Bobs at IRIS, but I'm the middle one, Bob Woodward. I'm the Director of Instrumentation Services at IRIS, and IRIS is the Incorporated Research Institutions for Seismology, and we're headquartered here in Washington, D.C. We have a number of different operations and activities, one of which I'm going to be talking about today, which is the NSF-funded EarthScope project. Hello?
We can hear you, Bob, but you did cut out momentarily.
Okay. Is the sound okay now?
Are you? Yep, it sounds fine now.
Okay. Sorry, I was trying to go back to get to my to the dialog box there on the Connect. Okay, we'll just interrupt if there's other problems, please.
Thank you.
So I will talk about the Transportable Array project, and this is just a quick overview of what I'll talk about. Obviously, the NSF Earth Sciences Division is funding this large project in Alaska. I'll give you a quick description of the project and highlight some results in solid Earth geophysics, but more importantly, I'll try to identify some ongoing efforts towards interdisciplinary science and adding capability. And then I'll touch a little bit on the process and mechanics that might be involved in interagency support of a project like this. So let me just jump into a bit of the background. I won't go through this in a great deal of detail. Transportable Array in Alaska, it's part of the NSF-funded EarthScope project. This was a MREFC project within NSF. We're in about the 13th year of a 15-year project. During the first 10 years, the Transportable Array, and I'll show you more about what the Transportable Array is in just a moment, but during the first 10 years, it's primarily focused on the lower 48. And then in the current 5-year block of EarthScope, we're really focused on Alaska and Northwest Canada. And you can see some of the funding levels that are involved here. And I've already talked a little bit about IRIS. IRIS itself is a nonprofit, and we're a consortium of about 120 universities that have research programs in seismology. So this is the TA in Alaska and Canada. Altogether, about 266 sites, about 85 kilometers between sites. And of course, we are primarily focused on putting in broadband seismometers. There are some other instruments. I'll be talking more about those. All of the sites have telemetry ranging from real-time, continuous real-time to episodic sort of store and then transmit, but always with 4 hours of latency or less. And in fact, in the first couple of years, we've been primarily running everything continuously. The color coding on the map shows where we are right now in terms of our deployment. So red symbols are active stations we've already deployed. Yellow ones are what we have remaining to do in the current work season. And then blue is the next work season, at which point the TA in Alaska and Canada will be fully deployed. So that's kind of the big picture. Now let me digress for a minute and contrast that with what we did in the lower 48 over the last 10 years. So we took a set of about 400 sensors and we rolled them across the country. Over the course of 10 years, we occupied all the sites indicated by triangles on this map. So it was about 1,700 sites over a period of 10 years, moving from the west coast to the east coast. So it was a major, major project. Unlike in the lower 48, where we kind of had a rolling deployment in Alaska, we're just gradually working at bringing up the entire network, and then it will all be running at the same time. For a bit of a digression, I'll just mention that we have had some previous success in multi-agency collaboration on the TA. In the case of the TA in the lower 48, we actually were able to create something called the Central and Eastern U.S. Network, which was a multi-agency collaboration to keep a number of the sites in the ground, keep them operating longer to meet multiple agency objectives. And so this was sort of an example widely cited of good government, of an efficient way to leverage NSF's original investment to achieve the or to meet the needs of multiple agencies. So with that, let me jump back to what we're doing specifically in Alaska. This is what one of our station sites looks like: a small fiberglass hut, solar panels. All of the electronics are inside the hut, and then the sensor is placed in a hole outside the hut. We emplace the sensor by drilling a hole with a helicopter portable drilling unit you can see in these pictures. We typically drill a 6-inch diameter hole. We drill about 3 to 5 meters either into soil or hard rock. And typically we can drill a site and install a station in one day. All of the sites that we're installing have already been visited for the purposes of obtaining and completing our permit applications. And at this point in time, virtually all the permits are in hand. So we're just busy this season and next season actually getting everything installed and in the ground. So again, just kind of coming back to the installation and I should say removal plan. So over the course of several years, we'll gradually get the 266 sites in the ground. We note that some of the sites are upgrades of existing seismic stations in Alaska. And then removal nominally begins in 2019 and continues into 2020. This is a finite duration experiment on the part of NSF, but certainly there's been some interest expressed in the possibility of extending the operation of some of these stations as sort of multidisciplinary autonomous observatories. So we can talk more about that at the end. So we've made a variety of visualizations of the data. I thought I'd go through these. Now these are primarily related to solid Earth, so I'm going to go through these just very quickly just to give you an idea of what seismologists are doing with the data. If you'd like to use these animations on your own, if you send me an email, I'm happy to provide the originals so that you can play them on your own machine. But this is perhaps the most typical thing, simplest visualization that we do, which is to look at the waves emanating from an earthquake. Let me go back and see if I can get this to play. So this is the Mineral, Virginia earthquake. I don't know if people can see this. The red and blue dots indicate up and down ground motion. Let me just stop that and go back and just start it again. And so you see these spherical wavefronts spreading out from Virginia. And again, these are the waves passing across the array. The symbols are plotted at the array locations. And we're just looking at up-down motion. And so it's the distortion of the wavefront due to heterogeneity in the medium that it's passing through that is, of course, of interest to seismologists studying the solid Earth. Looking at great earthquakes is a big part of what we do, and so this was the 8.8 earthquake off the coast of Chile. And let me see if I can get this video to start. This one's a 3-component video, so now we're looking at both up-down motion shown by red and blue, and we're looking at horizontal motion shown by the little tails on the symbols. And hopefully this is playing for everyone. And you can see the different kinds of waves sweeping across the array. And if we were sort of to slow this down and go through it frame by frame, you could see the details of the wavefront and see the kind of perturbations in the wavefront as it encounters the heterogeneity in the Earth. We can use the array as essentially an array or a telescope to look at distant earthquakes. So in this case, where the animation on the left is a visualization of the energy radiated by this large earthquake off the coast of Chile. And so the black line is the coastline of Chile, and what you're seeing when you see the colors start to evolve here, you're looking at the energy radiated by the earthquake. The brighter colors or redder colors are more energy. And so in this case, we're using the array located in North America to study the details of an earthquake rupture zone many thousands of kilometers away. So that kind of gave you an overview of what the solid Earth geophysicists are doing with the data. Now, I mean, those are just very simple visualizations, obviously, but hopefully they give a feel for the power of having this large distribution, spatial distribution of highly uniform sensors. And so what I'd like to talk about a little bit now is some of the other sensors that are on board of the stations and what's been done with those. So there is a simple MEMS barometer as part of each station. There's a precision barometer shown here by this Cetra 278. There's an infrasound sensor for low-frequency acoustic energy propagating through the atmosphere. And we're now in collaboration with NASA and NOAA installing these Vaisala meteorological packages onto the stations. And this is an example of what people have done with the pressure measurements. In this case, what you're looking at now is about 10 days of pressure fluctuations across the network. And this was at a time when there was a significant amount of tornado activity. And in a moment, you'll start seeing some red squares appearing, which were an outbreak of tornadoes. And in some cases, you'll actually see there'll be sort of a blast of tornadoes down here in the south, and you'll see pressure fluctuations propagating off across the network. Hopefully. So now, after all these tornadoes, you can actually see some coherent energy propagating from the south to the north across the array. And so, again, these are pressure fluctuations as measured at the transportable array stations, but it's just trying to give a sense of, again, the power of having this uniform, large area spatial distribution of sensors. And then finally, for something kind of completely different here, I'll play this, which is using the solar panel voltage as sort of a proxy for solar irradiance. Let me see if I can go back to that and get this to play. So now we're just seeing the blue colors are low voltage, the bright colors are high voltage, so you can just see these day-night oscillations, of course, in the solar panel output. But you actually start to see you can actually start to see the cloud cover migrating around over the array. If you look when it comes back into the daytime, you see small features propagating across the array. And in fact, if we take a snapshot, this is one example of a period of time on May 5th when you can see this strong storm moving in towards the Great Lakes. And you can see that as a very distinct low voltage area over the solar panels for the stations in that area. So can this be used for other purposes? I don't really know. I just put it in here to sort of stimulate people's thinking about what might be possible with some of these data. So coming back to the MET sensors, so this is an example of the way the sensors are deployed. The upper right photo shows in the warehouse, you can see a rod here that goes out, gets away from the HUD a little bit and goes up to the MET package. This was something that's kind of a mounting bracket worked out in consultation with NOAA. It's probably not ideal for a MET package, but it's probably, we hope, not a bad compromise given the realities of the stations that we need to install. But of course, as you can see in the lower right, some of the stations that accumulate significant snow accumulation. So as we get more of the stations installed, we'll find out just how much of the winter we are able to use the MET packages. All of the MET data flow in real time to Mesowest. They're all available to anybody can obtain a real-time feed of these data. I should say that all data produced by the Transportable array are completely open and are made available as soon as they're collected without restriction. The MET data are no different. We feed them into Mesowest, as that's a way that a lot of people like to get these data, but people can obtain data feeds directly if they want. Other sensors, we're looking at soil temperature profilers that we can put in as an adjunct to the stations, and we've done a few of those. We're starting to look at adding more of those, and also starting to explore the potential for adding webcams, both for monitoring volcano activity and for the FAA has a strong interest in the webcams that they use for sort of a pilot information system, I guess you could call it. And then some other things that are done with the seismic data, locating landslides is a possibility. The lower left shows a seismic recording made at a 70 kilometers distance from the large landslide shown on the right. So using the seismic data to make an assessment of landslides that would otherwise potentially be would go undetected is one possibility. Looking at ice cover is another. So let me just orient you to what you're looking at. So the yellow star is the northern coast of Alaska. You can see Alaska here, kind of a funny orientation with the Aleutians off to the left here. And on the right, you're looking at seismic power. And the red colors indicate much higher power. When the ice withdraws from the coast, we see much higher power of noise at our seismic station, and then as the ocean refreezes, you can see the station gets much, much quieter. So once the ice reaches the coastline, the seismic power that we see in the noise goes down substantially. And so as we install additional stations in the northern part of Alaska, we expect some very nice signal associated with the freeze-thaw cycle of the ocean, and just again an example of one of the things that can be done with the seismic data that's a little outside the normal realm of solid earth sciences. I think I'll skip this one, and just the point of it just being that this is not a unique observation, and we see this change in noise power at other coastal stations. And so we're looking forward to analyzing this in more detail. So last couple of slides, I'll just wrap up. EarthScope is supporting a very substantial deployment in Alaska and the Yukon, NSF EAR funding, primarily focused on solid earth imaging. But as I've tried to make the point with a number of the videos and the examples I've shown, we feel that the high-density spatial sampling has real value to a number of disciplines, and we'd like to continue to contemplate what sorts of additional sensors might be added to the station sites that could augment the science output of these stations. Tried to show some examples of some of the interdisciplinary observations that are being shown. And then finally, I'll just mention, I touched on this earlier, but whether it's synchronizing deployments or augmenting sensors or extending deployments, all of these sorts of coordination activities require a sharing of resources, and sometimes that's challenging both between disciplines and between agencies, and perhaps sometimes even within agencies. And we recognize that, and so we hope that by making presentations like this, we can stimulate people's thinking and explore new possibilities. And then this slide was just highlighting typically what's required for either interdisciplinary or interagency activities. Typically MOUs are involved, or perhaps using a service contract model. IRIS, as a nonprofit corporation, has some flexibility for the different kinds of contract vehicles or arrangements we can participate in. But of course, anything we do, we take to our sponsors at NSF to ensure that they're on board and feel that whatever we might be doing is compatible with their primary objectives. So with that, I'll leave some URLs on the screen, and hopefully my email address shows up in the IARPC web pages, and I'd be happy to answer questions now, or if you send me emails, I'm happy to respond in that way and provide further details.
Great, thanks so much, Bobby. I think maybe we have time for one quick question if anyone has questions.
Hi, this is Renee Tatusco. Can you hear me?
I can.
Hi, that was an excellent presentation, Bob. Thank you very much. For those on the phone and listening to this presentation, I did want to give you an update that we are planning an interagency workshop that will take place on Wednesday, Thursday, October 26th through 27th in the D.C. area. We're hoping that the ARCUS folks will be able to provide their conference facilities there on New York Avenue. And so we are in the process now of reaching out to senior leadership within the agencies to apprise them of this unique opportunity to maintain and sustain a very unique observing capability within Alaska. So I would certainly encourage you to get in touch with me if you have any questions about this proposed workshop, and if you have any suggestions for leadership within your agency that you think should be invited, I'd be very happy to take their names and email addresses. And Bob, I very much look forward to sharing this presentation with the new Federal Coordinator for Meteorology. Thank you.
Oh, fabulous.
Great, thanks so much, Renee. And if you need to track down Renee, I think it's easy for you all to find my email address. If you can't find Renee's, I think she's also on ARPC Collaborations. But feel free also, if you track me down, I'll get you in touch with Renee because it's a great opportunity. So great, thanks so much, Bob. That was fantastic. I love all those videos. It really, as a science geek, it really gets me excited, even if it's not my area. I know nothing about geophysics, but it's pretty cool stuff. So thanks so much for sharing that with us.
You're very welcome.